Welcome in Cairo. Now I'm going to continue our properties for light. Let's start by light diffraction. Pay attention with me, because light diffraction, it is very hard to happen. It is very hard to occur. Why? Think what? Why? First of all, you have see here light diffraction. We have here a source of light. Yes, it forms here Iris disk when it passes through a central bright spot. Here parallel rays, and the distance here is r. So what's meant by light diffraction? Light diffraction is the change in the direction of light, bending the light waves, changing the direction of light. But here the change in the direction of light happens in the case of when the light passes through a slit, but this slit is very narrow if it is compared to the wavelength. Why? Because the wavelength of light is ranged from 400 to 700 nanometers. So it's too short. Nanometer means 1 part of 10 power negative 9 meter. So it's too short. So to demonstrate, to show the light diffraction, it is very difficult, because it is very difficult to get an opening, narrower than the wavelength of light. So one of the conditions for the diffraction phenomenon, the main condition for the diffraction phenomenon, the wavelength must be greater than, yes, the size of opening, the size of a slit, the size of aperture. So here in light diffraction is a change in the direction of light propagation when passing through a narrow slit, very narrow slit, if it is compared to its wavelength or by a sharp solid edge. When a monochromatic source of light falls on a circular aperture, as you see in a screen, and the passing light is received on another screen, what do you see? We see bright, dark, circular fringes. These bright and dark circular surrounds at the center, at the middle, a bright spot, as you see. Here in the middle, bright spot. Here in the middle, bright spot. This bright spot is surrounded by bright and dark circular fringes. This pattern, the whole pattern, is called Iris disk. So what's meant by Iris disk? Iris disk, it is a bright and dark circular fringes surrounding the bright spot at the middle. That's for light diffraction. But I want to ask you, which is easier to observe it? Sound diffraction or light diffraction? First of all, you have to think, which is greater, the wavelength of sound or the wavelength of light? Of course, no comparison between the wavelength of sound and the wavelength of light. The wavelength of sound, as I told before that in chapter 2, is about 138 centimeters. But the wavelength of light ranges from 400 to 700 nanometers. So, and I said before, the main condition for occurrence, the diffraction phenomenon, the wavelength must be greater than the size of opening. The wavelength must be greater than the size of a slit or aperture. So, it is easier to realize sound diffraction in our life than light diffraction, because in diffraction phenomenon, the wavelength must be greater than the size of opening, lambda greater than size of opening. In case of sound, the wavelength is large, so it is easy to hear sound diffraction. But in case of light, the wavelength is too short, so it is hard to get a small opening shorter than the wavelength of light. That's for this point. After that, when I ask you about light as a wave motion, Why? Due to the following properties. Of course, light propagates in straight lines in all directions. Light propagates in straight lines in all directions in the same medium. Light reflects when meeting a reflecting surface. When light meets or when light falls on a reflecting surface, what will happen to the light? Of course, light is reflected. Also, light refracts. Light refracts when traveling between two media due to the change in the velocity. Don't forget, sine phi divided sine theta equals v1 over v2 equals lambda 1 over lambda 2 equals n2 over n1 equals 1 n2 equals 1 over 2 n1. Please don't forget it. It's a very important equation. Sine phi divided sine theta equals v1 over v2 equals lambda 1 over lambda 2 equals n2 over n1 equals 1 n2 relative refractive index from the first medium to the second medium equals 1 over 2 n1. Also, when light waves having the same frequency, same amplitude, same speed, but they interfere together. They propagate, yes, interfere, forming position of maximum displacement, maximum amplitude, reinforcement of light, bright fringes, and another positions, dark fringes, so it is light interference, superposition of two light waves, superposition of two identical light waves. Also, light diffracts. Light diffracts when passing through a narrow slit, very narrow slit. Lambda must be greater than the wavelength. So, a narrow slit or a narrow aperture compared with its wavelength or a by sharp solid edge. That's for the properties of a light wave. What's about the critical angle and total internal reflection? I want from you to see and concentrate very well in this. Here, water more dense, and here air is less dense. When a light ray passes from water to air, from water to air, which is greater in velocity? Of course, yes, the greater in velocity. Water is, it is difficult. The velocity of light in air is greater than the velocity of light in water. It is opposite to sound wave. Sound waves in chapter 2, sound travels in solids faster than liquid, faster than gases. But in light is the opposite. Here, the velocity of light in air is greater than. So when a light ray travels from water to air, so it reflects away from the normal. When we increase the angle of incidence in the more dense medium, what will happen? It reflects away, but it is tangent. It's grazing on the separating surface between water and air. It will be tangent. So, here the normal, here the tangent ray, here the bending ray. So, it makes an angle 90 degrees, right angle. So, this angle of incidence is called critical angle, phi c. It is symbolized by phi c, critical angle. It is angle of incidence in the more dense medium. That corresponds to an angle of refraction in the less dense medium, which is equals 90 degrees. This is the critical angle. Why we called it the critical angle? Because if we increase this critical angle, if light ray falls by an angle of incidence, greater than the critical angle, like this, it will happen total internal reflection. Angle of incidence equals angle of reflection. Angle of incidence equals angle of reflection. So, there is a total internal reflection. Light is totally reflected. And doesn't pass to the less dense medium. Light hasn't the ability to pass to the less dense medium. Light is totally reflected, is trapped in the more dense medium. So when a light ray passes from an optically denser medium of high absolute refractive index such as water or glass to a less dense medium such as air, a part is reflected, another part refracts, deviating away. As the angle of incidence increases, the angle of refraction increases. So, what's meant by critical angle? Critical angle, it is the angle of incidence in the optically denser medium that corresponds to an angle of refraction in the less dense medium equal to 90 degrees. Equals to 90 degrees, as the refracted ray grazing ray, tangent to the separating surface. But the total internal reflection, what happens? When the angle of incidence in the optically denser medium is greater than, exceeds the critical angle, so the light ray doesn't pass through to the less dense medium, but it is totally reflected. By applying Snell's law, N1 sin phi c equals N2 sin 90 degrees. Sin phi c equals N2 sin 90 degrees. So N1, yes, here equals, yes, N1 here means, yeah, for the water, sin phi c in the water, N2 here for air. So it equals 1. So N2 over N1 equals 1 N2 or sin phi c. If the air is the second medium, so N2 here equals 1. So sin phi c equals 1 over n. Sin phi c equals 1 over n. Or N1 equals 1 over sin phi c, where phi c the critical angle of the medium. At the end, I hope to understood total internal reflection, critical angle, sound diffraction is very important. Thank you and hope to join us in the next time, and goodbye.